This is a presentation of the extraction of caffeine experiment by Micheal Mikheal. In this experiment, caffeine will be extracted from tea leaves using the techniques of a solid-liquid extraction and a liquid-liquid extraction. The crude extracted caffeine will then be purified by sublimation, and its purity will be tested by melting point. This experiment required many materials and apparatuses. The first apparatus shown here is the solid liquid apparatus, in which you will need a 100 milliliter round bottom flask, a heating mantle, a water jacketed condenser, and tubes that will flow water in and out. The second apparatus shown here is of the liquid extraction, in which you will need a 100 milliliter separatory funnel. The third apparatus shown here is of the sublimation, and it will require a 25 milliliter vacuum filtration flask, a centrifuge tube, and the rubber band of the Hirsch funnel. The fourth apparatus shown here is the melt temp apparatus, which will be used to record the melting point of the purified caffeine. A vacuum filtration apparatus will also be used in this experiment. Caffeine, shown here, is a non-halogenated organic chemical and should be placed in the non-halogenated organic waste container. Methylene chloride, shown here, is a halogenated organic chemical containing chlorine and should be disposed of in the halogenated waste container. The first step in this experiment is the solid liquid extraction, in which tea leaves at the bottom of the round bottom flask are boiled in water and sodium carbonate. Caffeine is soluble in water and is more soluble in hot water, so the water is boiled, and a water jacketed condenser is added at the top of the round bottom flask in order to recondense water that may evaporate during the boiling. Water is also being replenished as it is being lost in this procedure. The sodium carbonate is added to the water to ensure that the caffeine and organic acids are deprotonated. This will allow the caffeine to be free to dissolve in the methylene chloride. The entire mixture is then vacuum filtered and remains looking like this picture shown here. The next step in this extraction is the liquid extraction, in which methylene chloride was added to the previous solution. Caffeine is soluble in hot water but is more soluble in methylene chloride. So methylene chloride was used to extract the caffeine from the water. This procedure was repeated 5 times since the caffeine is soluble in both the water layer shown above here and the methylene chloride layer shown here. After the caffeine is extracted from the water and into the methylene chloride shown here, a drying agent is added to the methylene chloride to remove any excess water that might have gotten into the methylene chloride. The methylene chloride is then evaporated and the caffeine remains in the flask shown here and here. The caffeine is still crude and is not yet pure enough for its melting point to be tested. As you can see here, the student made a mistake in evaporating the methylene chloride in the wrong flask. This flask had to be used in order to sublime the caffeine. The student quickly corrected his mistake by adding more methylene chloride into the flask and moving the methylene chloride solution into the right flask, then evaporating the methylene chloride again. The next step in this experiment is further purifying the caffeine through sublimation. Sublimation is when a chemical goes straight from the solid phase into the gaseous phase. Sublimation requires 2 conditions, which are low pressure and high temperature. As you can see in the flask here, it's attached to a vacuum, which allows the pressure of the flask to be very low. And also, a Bunsen burner is used to heat the flask, making the temperature very high in the flask. This allows the caffeine that was stuck to the walls of the flask to sublime into a gas and reach the point here on the test tube. The test tube was filled with ice and allowed the gaseous caffeine to recrystallize on the bottom of the test tube. It is more clearly shown here where the caffeine has recrystallized on the bottom of the test tube. And also, as you can see, some caffeine escaped into the vacuum right here, which was the main source of error in this experiment, in which the gaseous caffeine escaped into the vacuum and did not recrystallize on the bottom of the test tube. The caffeine is then scratched off from the bottom of the outside of the test tube and weighed. The final step in this experiment was determining the melting point of the purified caffeine to test its purity. In the capillary tube here is caffeine at the bottom, but the tube had to be closed off at the top with a flame because the caffeine would sublime inside of the melt-temp apparatus. In this experiment, the mass of purified caffeine that was recovered was 0.0089 grams of purified caffeine over the initial 1.51 grams of tea leaves at the beginning of the experiment, which gives a percent recovery of 0.59%. The recorded melting point of caffeine in this experiment was 236 degrees Celsius. This subtracted from the theoretical accepted value of 238 degrees over 238 degrees times 100 gives a percent error of 0.840 in the melting point of the purified caffeine. This is the HNMR spectra of caffeine, which shows 4 signals. Labeled next to it is the molecular structure of caffeine, where HA is the least deshielded over here, HB is a little more deshielded, HC is even more deshielded, and then HD is the most deshielded because it is connected to a double bonded carbon. The molecular formula for caffeine is CaH10N4O2, which gives an IHD of 6, meaning that there could be either 6 double bonds or 6 rings or in between. And as you see here, there are 2 rings and 4 double bonds, which add up to 6. The multiplicity of each of the equivalent hydrogen groups is singlet because none of the hydrogens have neighbors. The integration of the peaks are 3H, 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 and 1H, which is hidden here in the caffeine structure.